Greetings everyone! This video is dedicated to the Linear Optics Composer tool, the first one in the line of the forthcoming inventory of the LOQC.TECH project. I am now on the start page, which means I have already logged in via my Google account. Here you can see the list of my projects and the link called Library. Library is the place where the published user projects go to. Not so many of them now, since we are at the very start of the project's existence. Here you can observe what other people have created and copy whatever you like to your list of projects. So let's create a new project. Name, description, you can edit these anytime later. And let's proceed to the circuit design. In the Composer tool, you have numerous possibilities. Save and publish we'll discuss later. Now, in this group you have basic linear optics instruments. Beam splitter is parameterized by two parameters, reflection and phase shift. You can set both here. Phase shifter has the only parameter, the angle of the phase shift. All angles are in degrees. You can delete any object on the scheme by pressing the delete button. Then come three types of inputs. For a basic scheme it doesn't matter which one to use, so we are going to settle with basic input. The other two you will need for the conditional gate schemes in order to compute fidelities and probabilities. For an input you can specify the number of single photons coming from this input. And the single photon detection. You can also specify how many photons you expect here, so the simulation will omit all the results that don't match this outcome. Let's connect all of these. And save. Now, until you press the Save button, you can't simulate the scheme. And if you modify it later and simulate without saving, you'll obtain the result for the previous saved edition. After you save the circuit, it becomes available as a sub-circuit for your other projects. These sub-circuits are listed here. This one, for example, is the famous NSX gate. It is represented here by a small rectangle with three input and output modes, but its inner logic is more complicated, and it is implemented here. Okay, the circuit is ready. We have a symmetric beam splitter with two input photons in two modes, so I expect to observe the Hongu-Mandel effect here. Let's see. The Detail tab contains your project ID, which you might need when contacting the support. The Simulate tab. Let's press this button and behold the result. This might need a bit of clarification. What I see here is that I have two outcomes. These are their probability amplitudes, not normalized though. And for each outcome, there are squared creation operators in single mode. Creation operators on the output are encoded by a letter B, with the index, which is the number of the mode. Modes are enumerated from top to bottom, so we have either two photons on the upper detector or two photons on the lower detector. This is the Hongu-Mandel effect indeed. On the Matrix tab you can observe the direct and inverse transforms of the designed circuit. They are calculated during the simulation, so to obtain them you'll need to run the simulation first. and the fidelity tab. The fidelity is calculated assuming we have some conditional Pauli gate, which is not the case here. Thus, we get this disappointing message. Well, this is not the result one might expect from an explanatory video. So let's see some real conditional gate. I already implemented the gate CZ based on the NSX gate, both introduced by Knill, Laflamme and Milburn in this paper. So this is NSX. It employs only the basic optical instruments. Its main purpose is to change the sign of the amplitude for the state with 2 photons. Its matrix. Now here you see 2 gray inputs. Gray means they are ancillary. We must create 1 photon in the second mode and detect it also in the second mode. And I specify here that in the mode number 3 we must detect no photons. Only in this case the gate acts as intended. All other outcomes are erroneous, and the probability of the correct outcome is 1/4, which is obtained as the square of this amplitude here. Now, when we have this wonderful gate, we can use it in the design of the gate CZ. You can see there's 2 of them with their ancillas. And the green triangles designate the modes which encode the control qubit of the conditional gate. The creation operator in the upper mode encodes the state 1, while in the second mode here it would encode the state 0. So here we have the control qubit set to 1. Basic inputs encode the controlled qubit, and it is also in the state 1. For a conditional gate, you must have exactly 2 modes for both control and controlled qubits. Not more, not less. This allows the software to calculate the parameters of the gate. Here we see that the state 1,1 is transformed into -1,1 with probability 1 divided by 16. This is indeed the action of CZ based on 2 NSX gates, each producing the result with probability of 1/4. The matrices are quite frightening, and here you see the promised gate parameters for the computational basis. First of all, the gate is determined as the controlled Pauli Z. These are the probabilities for all basis states and the fidelities, which are surprisingly good. The bar charts depict the degradation of these parameters when we have 1 and 5% errors in beam splitter reflection parameter. For the infidelities, the logarithmic scale is used. Now, the last thing to notice is that you can't modify a published gate. You'll need to unpublish it first to see the save button. I believe this is starting to become a bit long for an introduction, so feel free to play and experiment with Composer yourself, and good luck with your research. Bye!